Indiana University and Purdue University, USA. He was an assistant professor of medicinal chemistry in National Institute of Pharmaceutical Education Research, Mohali. And after that, Sir joined the Department of Chemistry, Delhi University as a reader in July 2003. And later in March 2010, Sir was promoted to professor. And Sir became one of the youngest professor in the University of Delhi. Professor Rawat has published over 150 research papers, authored 2 books, 5 book chapters, and has 9 patents to his credit. His work has been cited over 4,975 times and with H index of 43. His research interest lies in the areas of development of small organic molecules such as anti-cancer, anti-malarial, antimicrobial, anti-Parkinson's agents, and nanocatalysis. Sir has supervised 24 PhD students. Professor Raut is an associate editor of National Scientific Reports, RSC Advances, and Everyman Science. And he has been a visiting professor at Japan Advanced Institute of Science and Technology, Japan. He is a member of various national funding agencies. Sir has a number of awards and honors to his name, out of which I'll just read out some, like CRSI Young Scientist Award, which Sir was awarded in the year 2007, ISCB Young Scientist Award, Professor D.P. Chakraborty 60th Birth Anniversary Commemoration Award, Mrs. Pratik Chinna Samman, Common University Nainital in the year 2011 was awarded to Sir, and many more are there. And Sir has a lot of experience in the administration also. And currently, Sir is Dean at Examinations in the University of Delhi. Sir has also experience of Dean works. Then he has been the chairman of governing body, then coordinator of MTech, provost Jubilee Hall, then also treasurer in Delhi University Students Union, and so and many more are there. But without taking more time of yours, I request resource person Professor Divan S. Rao sir to kindly start with today's lecture with the topic development of organic chemistry and its impact on human health. Thank you, sir.
Dr. Thanks to Dr. Dilip for your invitation. And it took me a while to respond to you because very recently I was given additional charge of Dean Examination in the University of Delhi. And we conducted this open book examination, and there are many issues with that. So I was busy with that, so I could not respond to you earlier. Today, actually, in the morning, I talked to.
That is fine, sir. You are welcome.
Yeah, thank you so much. I was told that most of the colleagues are from chemistry background, but in chemistry also, it's very difficult to deliver a talk on the research work because many of the people have different kind of specialization. So I thought to make it a little bit kind of a journal talk and to improve our basic journal knowledge about chemistry. So I chose a very normal kind of title, that is organic chemistry and its impact on human health. When we say organic chemistry, actually, as we know, okay, if you don't hear me sometime and if there is a slide problem, please just let me know, okay? Yeah, can you hear me?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
And slides are visible?
Yes, sir.
Okay. So when we talk about organic chemistry, as you know, organic chemistry starts with the synthesis of urea way back in 1828. And we all know that urea was synthesized by none other than Euler. But do you know, Euler was not a chemist. He was a medical doctor. But in 1823, he started studying chemistry as a minor subject. And Professor Gamlin took his minor substitute classes, and he realized that this person, Wheeler, has a very good knack of chemistry. So he advised him, Gamlin, to Wheeler to join Berzelius. And Berzelius was a world famed chemist at that time who has developed the hypothesis of vitalis, according to which at that particular point of time that organic compounds cannot be synthesized outside the living organism. That is the hypothesis what Berzelius gave. So when he started working on organic chemistry, the first thing what he did, he tried to make this compound, ammonium isocyanate. In fact, he got urea. That was a totally unexpected product. And if you look at ammonium cyanate and urea, both has same molecular formula. So it means what? It means it has 100% atom economy. If you know, nowadays, people talk about green chemistry, and green chemistry, one of the principles says all of the atoms of the starting material should reside in the product. So in this particular case, all of the atoms of the starting material goes to the product. So this is 100% atom economy reaction. So the very first reaction developed unintentionally by Wheeler was a green chemistry, fulfill the green chemistry principles. So what he did actually at that time, another thing is he laid down the concept of isomers also, because ammonium cyanate and urea have same molecular formula but different structure. Okay, and he did PhD with Berzelius, who taught that organic compounds cannot be synthesized in the lab. And first thing what he did to discredit the hypothesis of his own boss Berzelius. Later on, Adolphe Colbet synthesized acetic acid from carbon disulfide in 1845, and then it was proved undoubtedly that organic compounds can be synthesized in the laboratory. So this is a typical organic chemistry lab you can think of. So whenever you teach your students, we must teach them that the discovery of urea was made by Wheeler, maybe in these kind of laboratories. And from this lab, how this came to the textbook of the student, what they read now. So if you look at it, this is the original research paper Wheeler published in 1828. It is in German language. And from there, it came to the textbook. How it happens, as we all know, it is the publication, means the editors. So authors gets an idea, gets the experiments done, you have a result, compare the result, what new, conclusion, write the paper. Once you write the paper, you submit the paper. Submit the paper to the different journals. Who handles it? It handles by the editor. And editors now can decide whether your paper will be reviewed or not, means editor can reject it directly, or editor can say, yes, your paper has merit, it can be assigned to the reviewers. Now, it's the reviewer who gives you the good news or bad news based on their expertise on that field. So as an associate editor of scientific reports and RC advances, this is what I have been doing for quite some time now. And this is what it happens. When you submit a paper, it goes to the editor and we read it. Once you read it, and after that you decide whether the work is good enough to be published or not. If editor decides no, it is not good, so this is what we write. After careful evaluation of your manuscript, I regret to inform you that I don't find your manuscript suitable for publication in Royal Society Advances. That's one way. Another way, your paper is good, got reviewed, and it is accepted after revision. But are the editors that good to make a decision on someone's work? So one should not get disheartened if the research paper of someone get rejected through the reviewers or through the editors. Editors and reviewer can also make a mistake. I will give you a few examples of that. Some of the scientific papers that were rejected before going to win the Nobel Prize. Let me give the example. The first example is the Fermi paper and that was rejected by Nature, and the comment was too far from reality, and he got a Nobel Prize in 1938. Another one, Hans Krabbe's paper on citric acid cycle, which we read, citric acid cycle, which we teach to the students. This paper was accepted by the Nature, but the problem was at that time they had huge queue. So the editor wrote to Crab that if you want to wait that long, that's fine. If you don't want, you can submit your paper somewhere else. So what Crab wrote, the role of citric acid in intermediate metabolism of animal tissues. In 1953, Crab won the Nobel Prize for medicine. This was the comment from Nature. They said, yes, we accept it, but we have a queue, long queue. So it is better for you to submit your paper elsewhere. And this is what Crab did, and it got published and got a Nobel Prize. Next one, Gell-Mann's work. And this was very interesting actually. This was rejected by physical reviews, and the title of the paper was Curious Particle. And the editor did not like this curious particle. He suggested new unstable particle, which Gell-Mann did not like. So published their work somewhere else and got Nobel Prize in 1969 for physics. Higgs model, 1964. The physics later rejected this paper. It says it did not warrant rapid publication. Got Nobel Prize in 2013. Another beautiful work by this guy, Richard Arms, on NMR spectroscopy. It was rejected twice by Journal of Chemical Physics. Then they published it, and he got a Nobel Prize in 1991 in chemistry. So this is how it happens. Sometimes you write your paper, it gets rejected. So rejection always does not mean the quality of work is not good. It may be the problem with the editors and associate editors or the reviewers. So don't lose your heart if you get some rejection on your paper. Nobody knows what is stored for you. Well, coming back to the topic. So if I look at 19th century chemists, especially in organic chemistry, I would say the old Kohler, because he was the person who demonstrated that urea can be organic compound can be synthesized in the laboratory. Then came Kolbe. We all know one of the finest chemists of organic chemists of the century. Kekule, we all know, talked about the structure of benzene. Van 't Hoff and Liebel talk about the tetrahedral carbon. But I will give more emphasis on Kolbe because we teach Kolbe electrolysis, Kolbe synthesis of acetic acid and salicylic acid. And let me just give you brief introduction about Kolbe. Kolbe, as I said, was one of the biggest chemists of that time, and he was an editor of from 1870 to 1884 of the journal called Journal of Practical Chemistry. And what he used to do actually as an editor, any paper that comes to this journal, he used to look at it as an associate editor, as an editor of the journal. And if he rejects that paper without sending it to the reviewer, in the next edition, he used to write a commentary on those rejected papers. Unfortunately, his rejections were really bad in taste because later on, all those papers which he rejected were found to be laid down the foundation of organic chemistry in one way or the other. Some of his rejections were, he rejected the theory of Beer, who got Nobel Prize in 1905. What he wrote for Beer, Beer is an excellent experimenter, but he is only an empiricist, lacking sense and capabilities, and his interpretation of experimental data show particular deficiency in his familiarity with the principle of true science. He not only rejected the paper, and this is what he commented on Beer. What he wrote about calculus structure of benzene, he rejected that paper and wrote a commentary that says, when a young man with couple of research papers to his name criticized an old experienced chemist who started publishing papers when that young man was not even born, that testifies overconfidence and deficiency of modesty. So these were the violent languages which Colby used to use against the people whose work he rejected as an editor. We all know Kekule, and we have heard that Kekule saw a dream in which he talked about, the snake model. And this I also have heard, but I never came across a written document where it is written. As a science teacher, anything we teach in the classroom, we must see whether that exists in literature or not. Fortunately, I could get a paper that is published in Angewandter Chemie in 2015, and this is what it is written. So, in fact, Kekule saw a dream where he says, I was sitting there working on my textbook, but I was not going well. It was not going well. In my mind was on other things. I turned my chair towards the fireplace and sank into deep sleep. Again, the atoms fluttered before my eyes. This time, smaller groups remained modestly in the background. My mind's eye sharpened by repeated vision of similar kind and now distinguished larger form of the variety of shapes. Long lines, often combined more densely, everything in motion, twisting, turning like a snake. This is what Kolbe had to say. And this is the most important dream in the field of science, history of science. This is how he could solve the problem of, benzene. Now, when you are working on benzene structure, what we draw nowadays, it is a planar molecule. So this planarity of a benzene can you draw only when you know the carbon is tetrahedral. Okay, and during 1860s and 70s, two young men, one German and the French, were working in the laboratory of Tekle. One was Liebel, another was Van Hoff. So when they were working in his lab, they thought about tetrahedral carbon, which Kekule might have also thought, but because he was busy in his work on benzene structure, so he did not pay much attention to tetrahedral carbon. Both of these young men left to their respective countries, one to French and the German, and wrote a paper in 1874 independently, and they claim that they never met each other while working in the Kekule lab because Kekule lab was very big research group, and both of them talked about tetrahedral carbon. I will come that little bit later. So this is what Kekule said. The carbon compounds are organic compounds. Out of first 5 Nobel Prizes in chemistry, 3 were won by Kekule's student, Van Hoff, Fischer, and Bayer. Out of 5 first Nobel Prizes, 3 went to Kekule's student. Kekule died in 1896, so he could not get the Nobel Prize. Coming back again to Kolbe. So for Van Hoff and Liebel, what he said, this is a childish fantasy. So when these two young people published, that one was 22-year-old, another was 27-year-old at that time when they published the paper on tetrahedral carbon, and world famous chemist Kolbe criticized that paper very heavily. They said it's not possible, this is nothing but a childish fantasy. So the violence of his language worked unfairly to limit his reputation and eroded his career, earlier successful reputation as an organic chemist. So moral of the story is, no matter how big you are, you must be modest to your colleagues, to your peers. And his contribution is immense. He synthesized salicylic acid. And when we talk about organic chemistry, we talk about synthesis. Do you know who coined this term synthesis. It was Kolbe who coined the term synthesis during his attempted synthesis of acetic acid from carbon disulfide in 1845. And this is the first time when the term synthesis was written. And this synthesis we use till date. This is what the contribution of this man Kolbe. So the salicylic acid was synthesized by Kolbe, and it was utilized for the synthesis of acetylsalicylic acid, what we call aspirin, and it was synthesized first by Gilhard in 1853. He used acetyl chloride, and when you use acetyl chloride, you will have HCl as a side product, which is stoichiometric. And the method was modified later on by Hoffman. We use acetic anhydride to make the same compound. Now, if you look at the literature, people talk aspirin is synthesized by Hoffman, not Gilhard. Gilhard, nobody remember now. So this is what it happens. History remembers only the winners. So acetic aspirin is there because of Gilhard, but the method what we use till date is developed by Hoffman. This is how Hoffman is remembered by everybody. So what is the effect of development of chemistry in human life? So if you look at 1900, the average life at birth was little less than 23-year-old in India. Now 2000, it goes to about 65 years. Japan is the highest one. It's about 84, 85 now. So how that happened? This happened because the organic chemistry started developing. As a result, you get so many drugs. But let me just tell you the kind of problem we are facing today. This corona gave us the idea to understand if you don't have a drug to treat a disease, how fatal it can be, how bad it can be for a society. Because nobody could realize this, because at least of this generation of people, when there was no penicillin, what would have been the life of the people at that time? Today it is nothing. It is just a kind of one kind of sneezing problem, small virus problem. But bacterial infections are more serious than the viral infections. Since we don't have a drug, whole world is at ransom now. Whole world is stuck at one place. So this is what chemistry has done. Let me just to show you the life before penicillin. When there was no drug, this is what the life was. If you get any kind of bacterial infection, it won't get treated all, and people die. What happened to penicillin? We all know, if you ask this question as a general knowledge question in any of the examination, who discovered penicillin, everybody will say it is Alexander Fleming. It's Alexander Fleming, because this is what it is written in the textbooks also. Unfortunately, none of the authors did a justice to write correct things in the textbooks, nor the people who cited those papers. In fact, what happened, we all know the history. I will not go to the history of discovery of penicillin. Fleming published a paper in 1929 in British Journal of Experimental Pathology, wherein he claimed that it has antibacterial potential. The penicillin mold has antibacterial potential, but did not pursue this work after that. He did not work after that on this problem. It was Harvard Florey read his paper in 1938, wherein Fleming talked the antibacterial effect of penicillin notatum, and he got interested on this paper. He talked to his employer, Jane, and started working on this. And what he said, actually, he said that this was, when I started this work, it was the academic interest, the medicinal use was a bonus at the end of the day. So both of them started working on penicillin because Simon could not reproduce, could not isolate the penicillin. These people would isolate penicillin in small quantity and treated one of the British soldier called Albert Alexander. What happened? He was roaming in his garden and took out the rose uh, petals and put it in mouth, and that sprinkles his mouth, and it has a infection caused by streptococci and streptococci, and whole face was swollen and his eye has to be removed. Since the death was certain at that time, and these people have Flore and Chain had penicillin in their laboratory, and they requested the hospital which was next to their laboratory that they want to use this penicillin to treat Alexander, Albert Alexander. They met success, but quantity was not enough. He died. This is where the fourth person came in picture, that is called Norman Hatley. Norman Hatley was a person who developed a makeshift factory for the production of antibiotics, penicillin. And he did some work on this species, got a new species, and increased the yield to 1,000 times. And that resulted the rate dropped to 1% from 18% during World War I. But sole credit was given to Fleming. You know that, right? In the word of great Oxford pressure processor Henry Harris, without Fleming, no Chain, no Flore. Without Flore, no Hatley. Without Hatley, no penicillin. This was the contribution of this great man, to whom nobody knows, because our textbook writers never writes this. I wish we teach our student the correct things. So he got these three people got the Nobel Prize. I don't know why Hatley was left behind, but when I looked at the literature and the Nobel Prize rules and regulation, what I found that not more than three people can be given Nobel Prize in a group. That may be the reason of removing Hatley from it. These are the three people who got the Nobel Prize, and he got only two awards, Hatley. It was only in 1990, that is 45 years later of discovery of penicillin, he was awarded unusual distinction of honorary doctorate of medicine from Oxford University, to be given first non-medical person in Oxford's 800-year history. So this is what the story of penicillin. So this is how it looks like. This is from the Nobel lecture, and this is the picture of a baby infected with the bacterium. This is the baby treated by penicillin. This is how life goes. Another beautiful story is the discovery of artemisinin. In our country, actually, we always talk that we have natural flora and fauna, and most of them have wonderful medicinal properties. Our forefathers used those medicinal plants to treat their diseases. Unfortunately, we have not explored their medicinal potential as the way it should have been because of variety of reasons. But China started one program in 1950s. It was 1967, wherein they started exploring medicinal plants, and 2,000 Chinese herbs were investigated, out of which one of the plant extract isolated from Artemisia annua shows promises against the parasite growth of malaria, but it was not reproduced. And this is what is the problem in science. If you do something, it is not reproducible. It has no meaning. So the leader of that group, U22, read the ancient literature, the book called an Handbook of Prescription of Emergencies in 1574 AD. What it says a handful Qinghao immersed with 2 liters of water, bring out the juice and drink it out. And this is where it is written in this portion. So she thought maybe the extraction what they are doing, they were doing the hot extraction, maybe a cold extraction. So they did the cold extraction, result were reproducible, and they got the compound that we call artemisinin now, used for the treatment of malaria caused by Plasmodium falciparum. And this is the U22 in 1981. She got a Nobel Prize in Medicine in 2050 for the discovery of artemisinin. So why chemistry? Again, look at this. This molecule was isolated from marine sponge in 1950. From this to this, look at this. What is the difference? This OH is gone. This OH is converted to N3. This is called AGFT. Its market is 130 billion US dollar. First anti-HIV drug. So look at this drug here, thalidomide, that caused this kind of problem in the babies. We'll talk this little bit later. Now look at this. So if you compare this is 300 milligram per kg body weight. This is a toxic one also. 1959 to 1996. What is the difference? Cl substituted by H. This 6-member ring is thiophene. Rest of the structure same. The dose level is 5 to 10 milligram and with low toxicity. This molecule right here called thalidomide cause this kind of toxicity, but it can treat the leprosy later on. So chemistry will give the remedy of COVID as well. We have to wait for this. When we talk about the chemistry, there are downside of the chemistry also. If you look at these slides right here, this is the river in Ohio, and the picture is of 1969, and it is known as Burning River. One fine evening it caught a fire. Why? Because the industrial growth was just picking up at that time in United States. So every industry effluent, the useless material, was being either burned off to air or drained into the river. So river has all sorts of flammable materials, chemicals, and that caught a fire. Now today, this is how that river looks like, how clean it is. Unfortunately, this is what nature taught us as a human being, what we did. If you look at it, this photograph was taken in February 16, 2017 in Bangalore. You must have seen in the media reports. There is a fire. Again, the same problem. United States made their policies very clear about these kind of effluent treatments, but we didn't do anything. And this is in 2017. Bhopal gas tragedy we all know about. 25,000 people died, more than 5.5 lakhs people injured. Why that happened? It is not because of the chemistry, but it is because we practice chemistry wrongly. We put wrong people at a wrong place. Any person who is working in a chemistry laboratory must know the chemical nature or CAS of particular chemical before it is used in the reaction or in the plant. So what was the problem? Problem is the old attitude. What it says, by sensible definition of any byproduct in a chemical operation for which there is no profitable use is a waste. Okay. The most convenient, least expensive way of disposing the said waste up to chimney or down to the river is the best one. 1954. And this is what the approach was. But no, United States changed this attitude. Unfortunately, we are still practicing this attitude. But Terry Collin has says that chemistry has an important role to play in achieving the sustainable civilization on this earth. How can we do that? We can do that if you practice sustainability and green chemistry processes. What is this green chemistry? Let me just give you a small example of ibuprofen synthesis. This ibuprofen synthesis, the old one developed by Boots Company in 1960s, has 6 steps in all. And if you calculate the atom economy means all the atoms of the starting material ratio to the product. So the atom economy is 40%. So it means what? 60% atoms of the starting material goes as a waste, and that causes pollution. So if you develop any methodology by which you can increase this atom economy, your process will be called a green process. Let me show you that. Now, 1960 to 1993, 33 years later, a new synthesis was developed for the synthesis of ibuprofen. It has a 3 steps now. What is the atom economy? It is almost double. So this process is green in comparison to the process which was used in 1960s. So when we talk about drug discovery, it is never ending process. It costs a lot of money and time is about 15 to 18 years. Excuse me. And when organic chemist synthesizes about 10,000 compounds, one compound comes to the market as a drug. So the success rate you can understand, but still it is a good field to work on because you can contribute something for the welfare of the society. So if you look at the historical disasters, sulfonamide drug were used in 1937, considered to be the safer drug, but if you use in a huge quantity, this kind of toxicity can be there. But thalidomide was the biggest cause of worry for chemists and biologists alike, and that led to the development of FDA, though it was started from 1938, but regulation became more stringent after the thalidomide discovery, thalidomide toxicity issues. What was that? So as I said, in 1874, these two young men at that time, one was 22 year, another was 27-year-old, talked about tetrahedral carbon. When you talk about the tetrahedral carbon, it means what you are talking about. You are talking about the stereoisomerism as well. But nobody realized the importance of this stereochemistry in the biological system until the thalidomide disaster was reported. What was that? So how it affects, if you look at these two, fumaric acid and malic acid, one has a melting point higher, another is a lower. Cisplatin, transplatin, one is the drug, another doesn't work at all. So it means the geometry and the tetrahedral carbon affects the property of the molecules. So what happens actually, in 1957, this drug thalidomide was developed, and this drug was sold to 40 countries across the globe, and it was used for the treatment of morning sickness of pregnant women. But after 5-7 years, when data were collected, and the data was very catastrophic in a sense that more than 10,000 babies died. The expecting mother, whosoever took that medicine, either the babies died or those who survived had permanent disabilities like this. And nobody has an idea why that happened. But if you look at this structure here, so if you look at this carbon is chiral center. So when we say chiral center, it means it will have an enantiomer. One can be R and another can be S. One will have a positive, another will have a negative rotation. Okay? And this hydrogen right here can be above the plane or below the plane. Hydrogen is the smallest element of the periodic table. Above the plane and below the plane cause this kind of catastrophic effect in the biological system. And when you look at the chemistry of this is one enantiomer, another is this. So this is the effective enantiomer and this is the mutagenic enantiomer, and that caused the toxin. As a result, this was, I will just skip this. So this is how the babies who survived looks like this. And this was withdrawn from the market in 1962. And she was awarded by John F. Kennedy for her work on the withdrawal of thalidomide from the market. But late in 1990s, 1998, the same molecule was licensed for the treatment of one form of leprosy. WHO showed 99% patient improved significantly. It hailed wonder drug again. But you cannot prescribe this to a pregnant woman or expecting mothers. That's the key. So this is how it looks now. So you have a leprosy, it looks like this, it got treated, but don't forget these images. This is another views how the treatment goes with this drug. So what we work on at University of Delhi, I will just spend a couple of slides on this. We have been working on a concept called, hybrid drug diploma. What is this hybrid? So if you look at the literature, there are many molecules synthesized in the biological system. Like one of the best example you can think of is vinblastine and vincristine. These are two drugs used for the treatment of, cancer. Way back in 1960s, FDA approved these two. If you look at the structure of these two drugs, it has two alkaloids covalently bonded to each other. Both of those alkaloids were also isolated from the same plant, but those independently these two compounds shows poor anti-cancer activity. But when they hooked up together by a covalent bond, like compound A and compound B connected by a covalent bond, that becomes vincristine and vinblastine, and both are a drug. But this concept was not studied or utilized well. So what we did in this particular case, actually, this is a chloroquine, drug used for the treatment of malaria. This is a premethamine. This was used way back in 1960s. What we did here, we used this 4-amino quinoline part, this one, and from here we used this pyrimidine part and connected these two pharmacophores by a covalent bond here and synthesized the compound. What we found? We found this compound was 75 times better than chloroquine as antimalarial drug. Okay, not only that, it has a treatment rate of 80% to the infected mice in vivo model, and published this in 2012. Another molecule what we developed was based on a concept actually. That concept actually I will just show you how it works. So this is the molecule called amodiaquine. Okay, as I said, if you are working on a medicinal chemistry drug development program, out of 10,000 compounds, one comes to the market, number one. 15 to 17 years time it takes, average time. It costs about 450 million US dollars. So you can think how much costly affair it is. At the same time, you can think little bit more. If you develop a molecule, something like this, which comes to the market, but after a few years, you have to withdraw it because of the toxicity issues. You can think of what will be the fate of that pharma industry, right? And this is one of such example. This amodiaquine was used for the treatment of malaria, but later on it was withdrawn. Why it was withdrawn? Because it has a toxic effect on liver. Why this so? If you look at this part, para-aminophenol part, okay, this para-aminophenol undergoes for metabolism in the liver in presence of P450 cytochrome enzyme. It forms this kind of hydroquinone system, and this hydroquinone system is highly toxic to the liver. Okay, that's the liver toxicity. But this was already known in the literature in the form of paracetamol. Sorry, the structure is not correct. Okay, so in case of the paracetamol, you get this kind of metabolite. That was known, and this knowledge was not utilized while designing this molecule. So if you want to avoid this kind of toxic metabolite in the liver, what can you do? You either swipe the position of these two, bring this at third position, this at the fourth position, or substitute this by a smaller one, like fluorine, same size. What we did in this case, we used this pharmacophore and this portion was substituted from our earlier pharmacophore. This one. What happened? So we got, I'm not going to discuss the chemistry, what happens, how we synthesize. So this is the amodiapine, this is the molecule what we synthesize. So this portion OH and N-diethyl is substrate, rest of the molecule remains same. Well characterized by NMR and by mass spectrometry. Characterization complete. Now look at the in vivo activity of those molecules. 33 milligram per kg body weight, 100%. Chloroquine is very poor. Not only that, the compound has better T half than the amodiapine. It has to be because I showed you why it should be. It has a better clearance. We published in ACS Medicinal Chemistry just last year. And we have been working heavily on nanocatalysis also. Let me just tell you this. One of these molecules have entered into the phase 1 clinical trial for the treatment of Parkinson's disease. It was covered by Times of India in February 2020 also. I have not shown here. And we have been working on nanocatalysis, where we have made a substantial contribution last 5-6 years now. And this was made possible because I was lucky to have wonderful team of students with me. And now Shamsheer also has submitted a thesis, Sham is gone, Gunjan has submitted, Srishti, past all these people have, all up to 6, they have submitted the thesis. A few more people have joined. So this is what my research group is. And this is what our publication record now. And many of the papers recently got highlighted by Synfect, and this is the list. And with this, let me just show you a last slide. Before that, okay, this is the my research group, and this was clipped during Indian Science Congress in January 2020, where I was a sectional president. This was my research group at that time. And let me just show you who I am in this academic world, who are my ancestors. So I did PhD with Dr. D.S. Bhakuni from CDRI Lucknow, and Dr. Bhakuni did PhD with Derek Barton from Imperial College London. Barton did PhD with Helborn with Hunts with Wilkinson with Hertz, Rose, Berzelius, then Afjaus, Bergman, and Benjet Furner, 1751. I did a postdoc at Purdue University with Richard Gibbs. Gibbs did PhD in Okamara with Kurtz with Wood with Norris Ramsey, Fitting, Linchard, Wooler. Okay, so connected with the Wooler now. Gamlin and Benjet Furner. Look at it. This is United States lineage. This is the American lineage. The end person is one, so nobody knows who is connected to whom. Then I did a postdoc with Jeff Jaleski at Indiana University Bloomington. I could trace his lineage up to 1637. So this picture is in my office. Anybody visits to me, I always shows them this is my lineages. And thank you very much for your patience hearing and giving me an opportunity to speak to you something what I know about chemistry. Thank you very much.